When people talk about going to Mars, we're all pretty used to seeing diagrams like this floated about. You see the spaceship do a nice arced path between Earth and Mars. But have you ever stopped to think, why is it so convenient? Well, relatively convenient. What if instead of looking like this, the solar system looks more like this? Or instead of Earth and Mars moving like this, they moved more like this? It could be so much harder to go to Mars, but thanks to physics, it's actually not that bad. Here's why. Okay, so I know that going to Mars is by no means easy. Government agencies like the European Space Agency, NASA, and companies like SpaceX spend billions on missions into space, with Mars being one of the most challenging and expensive to do right now. It takes a lot of fuel to get a spacecraft into orbit around Earth, and it takes even more to get a spaceship from Earth orbit to Mars orbit. I am not disputing any of this. That being said, it could be a lot worse for going to Mars. In their current orbits, Earth and Mars orbit the same way around the Sun. This is called Retrograde. Mars's orbit also makes a roughly 2-degree angle with ours, so we're fairly well aligned. While keeping both planets at their current distance from the Sun, this is pretty much the best orientation we could have for going to Mars. To take a spacecraft from Earth to Mars, we do what are called orbital maneuvers. These involve firing rockets to change the speed and direction, or velocity, of the spacecraft. The change in speed for a given maneuver is measured using a quantity known as delta V, which is how much we change the impulse per unit mass of the spacecraft. Or, in practice, how much we change its speed. Currently, we have to change the speed of a spacecraft by about 4.3 kilometers per second to move it from a low Earth orbit to a Mars transfer orbit, the orbit needed to get a spacecraft from Earth to Mars. But we still have to slow down. That takes approximately 2.7 kilometers per second of delta V. All in all, we need about 7 kilometers per second, or 15,700 miles per hour of delta V to take a spacecraft from low Earth orbit to low Mars orbit. But what if instead of being roughly aligned with our orbit, we rotated Mars 90 degrees to be in a roughly polar orbit around the Sun? We'll keep the orbital distances of Earth and Mars the same as they are now, so both planets would be as we expect them to be, and no oceans get boiled off. To calculate the delta V needed to move to Mars now, we need to use this equation. In this equation, Vi is the starting velocity, Vf is the final velocity, and theta, that Greek symbol at the end, is the angle that we need to change. Now, Vi is Earth's orbital speed around the Sun, 30 kilometers per second or thereabouts. Vf is Mars's orbital speed around the Sun, so about 24 kilometers per second. And since theta is equal to 90 degrees, that final term just falls away because cos of 90 degrees is 0. So using this equation, the orbital inclination change of our spacecraft needs about 38.4 kilometers per second of delta V. But we're not done yet. We still need to slow down and get into a low Mars orbit. So we need to whack on that 2.7 kilometers per second again. When we do that, we land on a total delta V of 41.1 kilometers per second. That's quite an increase, but it's actually not the worst we could be dealing with. The worst situation we could be dealing with is this. Earth is unchanged in its orbit. We're still going around the Sun at about 30 kilometers per second. But Mars is completely reversed. It's still going at 24 kilometers per second around the Sun, but it's going the other way. This is called retrograde, and it's actually the worst situation we could have. To get to Mars, we still need to do the low Earth orbit to low Mars orbit maneuvers, so that's that 7 kilometers per second we talked about earlier. But we also have to turn around. Now, Earth is moving at about 30 kilometers per second around the Sun. Mars is moving at 24 kilometers per second around the Sun the other way. So we have to essentially stop in space. We have to slow down from 30 kilometers per second to 0, and then speed up again to 30 kilometers per second the other way in the direction that Mars is orbiting. Then we do our 7 kilometers per second maneuver. This lands us on a total delta V of 67 kilometers per second. That's an insane amount of delta V. So if our current orientation is so ideal, how did we get so lucky? The simple answer? Physics. To be a little bit more accurate, we have to talk about how stars, and by extension planets, form. Stars come from huge clouds of dust and gas, known as molecular clouds. These are made up of around 99% gas, most of which is hydrogen, and about 1% of dust. These clouds can sit fairly undisturbed for a long time, but when they are, for example by a supernova explosion, we get pockets of higher density that start to cause the cloud to collapse, starting star formation. A topic for a future video. What we're interested in though is the small amount of rotation that the cloud has before it starts to collapse. Here, we need to consider something known as the law of conservation of angular momentum, one of the many brainchilds of British mathematician Sir Isaac Newton. The law of conservation of angular momentum states that the total angular momentum of a system both before and after an interaction is constant. What this means is that as the cloud collapses, the angular momentum of the entire cloud is constant. Now, angular momentum per unit mass is the product of velocity and distance from the centre of rotation, which in this case is the forming star. Since the orbital distance is decreasing, the gas must speed up. This causes it to accelerate outwards and flatten into a disk. Gravity then exerts what's known as a centripetal force to stop it just flinging it off into the void. It's at this point that planets begin to form in the disk. And since the disk all orbits around the Sun in the same way, the planets form and all orbit around the Sun in roughly the same way. And since the disk is approximately flat, they all form with roughly the same inclination. This is what gives us the solar system we all know and love, even gives us Pluto. It's some simple physics from over a century ago. Now, if you found this as fascinating as I did the first time I learned about it, then please hit that like button and subscribe so you don't miss my next video. And if you have any comments, questions, criticisms, or topics you'd like me to cover in a future video, please leave them in the comment section while you're down there. In the meantime though, I've been Thomas, this has been Inversion Science, and I'll see you in my next video.